Let us now look at some examples of games and Nash equilibria in those games. So here's the first game, a familiar game. This is, of course, the prisoner's dilemma. If both prisoners cooperate and then they get a light punishment, and if they do not cooperate, they get a more severe punishment. If the one cooperates and the other does not, then the cooperator gets a terrible punishment, and the one that does not cooperate gets off scot-free. Now, of course, this game has a dominant strategy to defect. No matter what the other agent does, you're better off not cooperating. And so, of course, the only dominant strategy outcome is this one of both defecting. And indeed, that is the only Nash equilibrium in this game. So it's a Nash equilibrium. It's the best response. If the other person defects, then it's the best response to defect. But in fact, it's much stronger than that. It's best to defect no matter what the other agent does. So this is an example of one unique Nash equilibrium that happens to be a very strong one, a dominant strategy, Nash equilibrium. So here's another game. This is a game of pure coordination. Think of it as walking towards each other on the sidewalk, and you both can decide whether to go to your respective lefts or your respective rights. In both cases, you will do fine and you will not collide. And of course, if you miscoordinate, if one goes to the left and the other to the right, you will collide. So this is a natural game, and in fact, you see that you have two Nash equilibria. The one that I wrote down here. If one of the players goes to the left, it's the best response to go to the left, and conversely, if the other player goes to the right, you're best off going to the right as well. And the others are not Nash equilibria. So here's an example of a game where there are two Nash equilibria, or two specifically pure strategy Nash equilibria. Again, we'll discuss why we call these pure strategy later on. Here's a very different game. This is often called the game of Battle of the Sexes. Imagine a couple, and they want to go together to a movie, and they're considering two movies. One of them a very violent movie, Battle of the Titans, and the other a very relaxed movie about flower growing, called these B and F. The wife, of course, would prefer to go to Battle of the Titans, and the husband would prefer to watch flower growing. But more than anything else, they would want to go together. And so here are the payoffs. If they both go to Battle of the Titans, then they're both positively happy, the wife more than the husband. If they both go to the flower growing movie, then the husband is slightly happier than the wife. But if they go to different movies, neither of them is happy. That's the game. How many equilibria do we have here? Well, again, we have two pure strategy Nash equilibria. Why is that? Well, if either of them goes to the Battle of the Titans, then the other one would want to go there too, because if they go to a different one, they would get 0 rather than whatever they get here, 1 or 2, depending on whether they're husband or the wife. And conversely, on the flower watching movie, flower grow movie. And so in both cases, the best response is to go to the movie selected by the other party. So on the face of it, it looks very similar to the game of pure coordination that we have here, but we do see a slight difference here, and we'll revisit that later on when we speak about not pure strategies, but mixed strategies. Here's another example, the last one we'll look at, and this is the game called Matching Pennies. Imagine each of us, two players, needing to decide on some side of a coin, heads or tail. If we decide on the same sides, heads or tail, but we decide on the same one, then I win. If we decide on different sides, you heads and me tails, or vice versa, then you win. And so we see this here. If we both decide on heads or we both decide on tails, I win, and otherwise you win. By winning, I mean I get 1, you get -1. So this is a zero-sum game. The sum of our payoffs is 0. What is a pure strategy Nash equilibrium here? Well, let's think about it. Suppose I pick head. What is your best response? Well, your best response then is to pick tails, because you get 1 rather than -1. But if you pick tails, then my best response is now to play tail, because I want to coordinate with you, because then I will get 1 rather than -1 that I would be getting here. But now if I play tails, you'd rather play heads, because you'd get 1 rather than the -1 you're getting here. But again, if you're playing tails, if you're playing heads, I want to play heads to match. So we have this cycle where the best responses are leading us in the cycle. And so there is no pure strategy Nash equilibrium in this game of matching pennies.
So this video is going to describe an important property that some games have, which is called dominant strategies. To begin with, I'm going to start using this word strategy that we haven't defined yet, and indeed, you're not going to get a definition for a little while. So to begin with, when I use the word strategy, I want you to understand this just to mean choosing some action. This name, in the end, is going to be what we call a pure strategy, and it's going to turn out that there's another kind of strategy that I haven't told you about yet, and everything in this lecture is also going to apply to that kind of strategy, but it's not going to matter for you right now. So let's just understand strategy to mean choice of action. So let's let SI and SI prime be two different strategies that player I could take, and let's let capital S minus I be the set of all of the other things that everybody else could do. I'm going to define two different definitions of what it means to say that SI dominates S prime I. So first we have the notion of strict dominance. And here I'm going to say that SI strictly dominates S prime I if it's the case that for every other strategy profile of the other agents, in other words, for every other thing that they could do, for every other joint set of actions that they could take, the utility that player I gets when he plays SI is more than the utility that I gets when he plays S prime I. So, in other words, it might matter to player I what everybody else does. That might affect his utility. But it will always be the case that he's happier when he plays SI than he is when he plays S prime I. And in fact, he's strictly happier because we have a strict inequality here. So he's going to get strictly more utility by playing SI than by playing S prime I. That means that SI strictly dominates S prime I. Now, we have another notion of dominance, which I call very weak dominance. It's almost the same definition, as you will have noticed. The only difference here is that I have a weak inequality instead of a strict inequality. And so what this is saying is, no matter what everybody else does, I'm always at least as happy playing SI as I am playing S prime I. And when that's true, I say that SI very weakly dominates S prime I. Now, you might wonder why I have this name very weak. That's because this condition even allows for equality. So even if it's the case that SI and S prime I are always exactly the same as each other, I'm still allowed to say that SI dominates SI prime. And that sounds like a strong thing to say about equality, so we soften it by saying it's very weak dominance. Now, in fact, there are also some other kinds of dominance that kind of live in between these two that are not quite as strong as strict dominance and not quite as weak as very weak dominance, but they're not important for us right now, so I won't mention them. Well, what is important about dominance? Intuitively, when one strategy dominates another strategy, then I don't really have to think about what the other agents are going to do in order to decide that I prefer to play SI than to play SI prime. Because I know that my utility is never worse by playing SI, so regardless of the kind of dominance, it's sort of a good idea for me just to play SI. Now, this can get even stronger if one strategy dominates all of the other strategies. In that case, then this one strategy, SI, is kind of better than everything else. And in that case, I can say not just that it dominates something, but I can say that it's dominant, that it's just kind of the best thing to do. And if I have a dominant strategy, then basically I don't have to worry about what the other agents are doing in the game at all. I can just play my dominant strategy, and that's going to be the best thing for me to do. Now, formalizing that notion that this is just the best thing to do, I can claim to you, and it's not hard to see that it's true, that a strategy profile in which everybody is playing a dominant strategy has to be a Nash equilibrium. So if everyone is playing a dominant strategy, then we've just got a Nash equilibrium because none of us wants to change what we're doing. We already know from the fact that the strategy is dominant that there's nothing better for me to do. Furthermore, if we all have strictly dominant strategies, then this equilibrium has got to be unique because there can't be two equilibria in strictly dominant strategies because that would mean we prefer these strategies to each other strictly, and that just can't happen. So lastly, I want to think about the prisoner's dilemma game. And I want to argue to you that the players have a dominant strategy in this game. So I want to claim to you that player 1 has the dominant strategy of playing D. And I'm going to do this by a case analysis. So let's begin by considering the case where player 2 plays C. If player 2 plays C, then player 1 is really thinking about this column of the matrix. He knows he's in this column. And that means he faces a choice between getting a payoff of -1 and getting a payoff of 0. And 0 is bigger than -1, and so player 1 would prefer to get 0, which means that his best response to C is to play D. On the other hand, let's consider the case where player 2 is playing D. In this case, player 1 finds himself in this green column, and that's kind of too bad for him because now he faces a choice between the payoff of -4 and a payoff of -3. And both of these numbers are smaller than the numbers that he had a choice about before, so he likes the blue column better than he likes the green column. But if he is in the green column, he still prefers to get -3 than to get -4. And that means, in this case, he again prefers to play D. So we can see that regardless of what player 2 does, player 1 best responds by playing D. And in both cases, his preference was strict. And that means he has a strictly dominant strategy in this case. And so D is a dominant strategy here. I'll leave it to you to see that the same thing is true if I argue that player 2 has a dominant strategy of playing D, and I do a case analysis about what player 1 can do. But the game is symmetric, so the same argument goes through there as well. This video is going to tell you about the concept of Pareto optimality. So far, we've thought about some canonical games from game theory, and we've thought about how to play them. But we've really been taking the player's perspective. We've been thinking about what is the right thing to do in a game. Now I'd like to instead step back and think about the games from the perspective of kind of an outside observer looking in and trying to judge what's happening. And the question that I'd like to ask is there a sense in which I can say that some outcomes of a game are better than other outcomes? I'd like to encourage you to pause the video at this point and just think about this for yourself. See if you can come up with an answer before I tell you what my answer is. Well, let me give you a bit of a hint. You can't say that one agent's interests are more important than another agent's interests because I don't know how important the different agents are, and actually it turns out I can't even say what scales their utilities are expressed in. There isn't necessarily a common scale for utility between the different agents. And so, in a sense, the problem of evaluating an outcome of a game is kind of like trying to find the payoff maximizing outcome when I'm going to be paid an amount in different currencies, and I don't know what these currencies are. So you can kind of think of the outcome of a game as an outside observer, just interested in kind of social good of the participants, as kind of being like an outcome where I get player one's payoff in currency 1, and I get player 2's payoff in currency 2, and nobody can tell me what the exchange rate is between currency 1 and currency 2. Now that I've made this a little bit more concrete, let me again invite you to think about whether there's a way that I can identify outcomes that I would prefer one to another. Well, here's a way we can make this work. We can't do it all the time, but sometimes there's an outcome O that is at least as good for everybody as some other outcome O prime. Remember, an outcome is like a cell of the matrix game. So I've got this matrix game, and there's some outcome O which is at least as good for everybody as some other outcome O prime. And furthermore, there's some agent who strictly prefers O to O prime. Well, in that case, I should be, so let me actually make an example of this. So O might be that player 1 gets 7 units of utility and player 2 gets 8. And O prime might be that player 1 gets 7 units of utility and player 2 gets 2 units of utility. In this case, O is at least as good for everybody, and because it's equal for player 1, and it's strictly better for somebody. It's strictly better for player 2. So in this case, it seems reasonable to say that an outside observer should feel that outcome O is better than outcome O prime. And technically, the way we say this is that outcome O Pareto dominates O prime. Well, now I can define this concept of Pareto optimality. An outcome O star is Pareto optimal if it isn't Pareto dominated by anything. So that's kind of a hard definition because it's defined in negative terms. Let me say it again. An outcome O star is Pareto optimal if it isn't Pareto dominated by anything else. So there's nothing else that I can prefer to it. So let's test our understanding of this definition by asking a couple of questions. Is it possible for a game to have more than one Pareto optimal outcome? As always, let me encourage you to think about this for a second before I answer it. Of course it is, because it's possible for two outcomes to neither Pareto dominate each other. If, for example, all payoffs in the game are the same, if I have a game where everyone gets a payoff of 1 no matter what happens, then nothing dominates anything else, because domination requires somebody to strictly prefer something to something else. So this game has more than one Pareto optimal outcome. Something else I could ask is, does every game have at least one Pareto optimal outcome? Or is it possible that just nothing will be Pareto optimal? Well, I'll let you think about it for a second, but the answer is yes. Every game has to have at least one Pareto optimal outcome. This is easy to see because in order for something to not be Pareto optimal, it has to be dominated by something else. So in order for there to be no Pareto optimal outcomes in a game, we would need to have a cycle in Pareto dominance. We would need to have it be the case that everything is Pareto dominated by something different. And it's pretty easy to persuade yourself that we can't have cycles with Pareto dominance. The reason we can't have cycles is just the way the Pareto dominance is defined, that in order for something to be Pareto dominated, it has to be at least as good for everybody and strictly preferred by somebody. And I'll leave this to you to think about, but that definition implies that there can't be cycles in the Pareto dominance relationship. So finally, let's look at our example games that we've thought about and identify Pareto optimal outcomes. And in each case, I won't say this every time, but I encourage you to pause the video when I've put up a game, think for yourself about what the Pareto optimal outcomes are, and then I'll identify them for you. So first of all, we have the coordination game. And here, these two outcomes are both Pareto optimal. In the Battle of the Sexes game, these two outcomes, again, are Pareto optimal. The change in payoffs here doesn't make a difference. In the Matching Pennies game, this one's a bit trickier. I'll let you think about it for a minute. Every outcome is Pareto optimal because there's no pair of outcomes where everybody likes the two outcomes equally well. There's always kind of a strict trade-off that happens because the game is zero-sum. And this is generally true of zero-sum games, that every outcome in a zero-sum game is going to be Pareto optimal. Finally, here we have the Prisoner's Dilemma game. And let me also let you think about this one. Turns out here, all but one outcome is Pareto optimal. This outcome is not Pareto optimal because it is Pareto dominated by this outcome. And now, I'm ready to give you a punchline that we've been building to for a while about the Prisoner's Dilemma game. Here's why the Prisoner's Dilemma is such a dilemma. The Nash equilibrium of the Prisoner's Dilemma, which in fact is a Nash equilibrium in dominant strategies, so it's the strongest kind of Nash equilibrium there is. There's a Nash equilibrium in this game. In fact, everybody should play this equilibrium even without knowing what the other person is going to do. I can be sure that I should play my strict dominant strategy in this game, get to this outcome, and that is the only non-Pareto optimal outcome in this game. So almost everything in this game is kind of good from a social perspective, and the only other thing in the game is the thing that we strongly predict ought to happen. So that's why we think the Prisoner's Dilemma is such a dilemma.